Hello everyone. Consider a box at rest on a floor with some friction. There's friction between the box and the floor. What would I have to do to get the box to accelerate uniformly? Well, of course, I'd have to apply some force, right? But don't forget, there's also some friction which would oppose that motion. So if I want the box to move, what has to be true about these forces? If I want it to accelerate, well, the applied force would have to be bigger than the force of kinetic friction. Right? And then that net force would make it accelerate. And if those forces are constant, then the net force is constant, and then the resulting acceleration would be uniform or constant, if you will. Right? And this is, of course, what we call Newton's second law. Right? We did a whole big long lab back a few units, or actually last year, in which we found that the net force was equal to the mass of the object times its acceleration. Right? And this is the linear version of Newton's second law. Well, then that kind of begs the question, is there a rotational version of Newton's second law? Right? Something that we can use to see why do objects rotate with uniform angular acceleration. Well, let's consider the equipment we've been using. And of course, in order to make that equipment accelerate rotationally, angularly, if you will, we need to apply a force, but not just anywhere. We need to apply the force somewhere away from the axis of rotation so that that force provides what we've been calling a torque. And if there's a net torque, it'll make it angularly accelerate. Right? So we have to have a force that applies a net torque that results in an angular acceleration. What factors do you think will affect how much angular acceleration we have? Well, the obvious one is how big the torque is. That's a fairly complex thing, remember, so we'll talk a little bit about that. Now, if you think about the linear analogy, F equals ma, right? It was about what determined how much it accelerated. Well, it was the force, but it was also the mass. The mass had to do with the inertia of the object, right? But in this case, everything with rotation is more complex. So I'm not going to say it's just mass, but it is something about the mass, all right? Because we don't know exactly what something that is, and we're going to actually do a set of labs in order to figure this out over the next week or two, we're just going to leave that something about the mass constant all the time. All right, we're going to use the same masses. We're going to leave them in the same spot on the equipment, on the outside, like I showed you in the diagram, and we're going to leave them there the whole time so that we don't change anything so it doesn't affect the lab. So basically, our lab is going to be to figure out the relationship between torque and angular acceleration with constant mass. Right? We're going to create graphical and mathematical representations of that relationship. So we're going to keep everything about the mass constant, and then we're going to see, is there a relationship between torque and angular acceleration and what that is, and math models, and what slope means, and all that good stuff. Okay? So, how we're going to do that? Well, of course, you guys are doing a pivot, and this is kind of the way the pivot's set up. I'll play the movie in a moment here. You'll notice there's a wheel, right? And around that wheel, there's a string wrapped, and then there's masses hanging off the side. This guy's going to cut this string, which is going to get it going. So let me show you here. All right, now down at the bottom, you can change some things. You can change the type of wheel, although we're going to keep ours constant. All right, we're going to use that top one. And then you can change the hanging mass. Lots of different ones. So I'm going to change it to 100. So right now there's 100 grams hanging off the side, 0.100 kilograms. Right? And if we run it, you'll notice when he cuts the cord, it starts to accelerate angularly. Or the masses accelerate as they fall, and the wheel accelerates rotationally. Over here, we've got a couple things we can use. There's a little ruler, which you're going to put just on the bottom of the mass. Okay, the 0. And then we're going to take the stopwatch. We're going to find the frame where he cuts the cord, cuts the wire. Once we find the exact frame where he cuts it, that's where we are going to 0 the stopwatch. See how the stopwatch now reads 0? And then we're going to let it run and time how long it takes it to accelerate through 40 centimeters, as exact as we possibly can. And then that time on the stopwatch will be the time that we'll use. Make sense? Once we have that, right? We can use the displacement, the 40 centimeters or 0.40 meters, right? And the stopwatch time, right? We can use that to calculate the acceleration of the masses, okay? The acceleration of the falling masses here. And of course, we will do that, much as we did in some of the other labs with pivot, by using the ever-popular third kinematic equation, where the masses start at rest, so that term drops out, and if we solve, right, we'll find the acceleration by taking 2 times the displacement, which in every trial is going to be 0.40 meters, right, and dividing it by the time squared. Don't forget the squared, right? You forget the squared, then we'll be in a bit of trouble there getting the right results. Right, so that is how we'll use the video to figure out the acceleration of these masses, the linear acceleration of the masses, for a bunch of different hanging masses. Right, bunch of different masses. And those are all listed, right, on your lab sheet. Of course, the lab sheet's a big help here. So, how is that going to help us find our variables? And remember, we're trying to do torque and angular acceleration. Well, here's the hanging masses. This is actually what it looks like in the apparatus the class is using, right? A little mass hanger with some masses on it. What forces act on those masses? Of course, gravity acting down and the tension acting up. Right? How big are those forces? Well, they can't balance, and this is a very common error when analyzing this situation. Right? The forces can't balance because if they did, it wouldn't accelerate. It might move, but it would move constantly, right? Zero acceleration. So, since the masses are accelerating down, the force of gravity has got to be bigger than the tension. Is everybody with me there? Again, the common mistake is that people set this up and they go, oh, the tension in the string will just be equal to the weight of the masses. No. In fact, because it's accelerating, it's the net force is equal to the mass times the acceleration, right, of those masses. And we now know the acceleration. That's what we got out of the pivot. So the net force would be tension, which is up, so positive, minus gravity, which is down, so negative. And notice here I also did another little tricky thing. Do you notice how there's no arrow on any of these anymore? Right? That's because I put in the directions. So tension is up, positive, gravity is down, negative, and the acceleration of these masses are down, so also negative. Very important to turn it into a scalar equation here. Okay, so this is force of tension minus force of gravity equals negative mass times the acceleration of the masses. Solve for the force of tension. We get force of gravity minus ma. And as we well know, we can find the weight of objects here on the surface of the Earth by taking the mass times the gravitational field strength. And if you want to get a little fancy, right, we can calculate the force of tension by taking those hanging masses and multiplying by the quantity gravitational field strength minus the acceleration that we calculate from the video. So this will give us the force of tension. Now, this is still not the angular acceleration or the torque, but this is a step along the way, okay? There's a lot going on in this lab, a lot of calculations to make. So let's start with the angular acceleration. This is an alpha. Right, be careful. That's an A. Okay, this is an alpha, angular acceleration. Well, the key thing here is to realize that this apparatus works pretty ideally in the sense that as the string pulls off of the pulley, and we're going to use the wheel pulley, right? It doesn't slip, right, on that pulley at all, right? There's no slipping going on. What does that tell us? Well, if the string doesn't slip on the pulley, what has to be true about the acceleration, the linear acceleration of the masses, and the linear acceleration of the outside of the pulley? You say that again. How does the motion of the outside of the pulley have to compare to the motion of the masses if the string isn't slipping on the pulley? And hopefully you can see that it has to be the same, right? The outside of the pulley and the string, which is attached to the masses, have to be moving the same speed with the same acceleration, right? Otherwise, the string would slip on the pulley. So that means we can relate the acceleration of the masses that we can get from taking data in the video and using the third kinematic equation to the tangential acceleration of the outside of the pulley. And we know how to calculate the tangential acceleration of the outside of the pulley. It's angular acceleration times the radius, I'm sorry, that should say the wheel, but, of the wheel. I guess it's a pulley, right? It's just a big wheel pulley. And one step of algebra, and this is how we can calculate the angular acceleration. We can take that tangential acceleration of the pulley, which is the acceleration of the masses, same number, right? Divide it by the radius of the wheel, which I will give you on your lab sheet. It's like 0.319 meters. It's like 31.9 centimeters, all right? But that's going to be the radius of the wheel, all right? So that'll be given to you. So we can take the acceleration we find in the lab, in the pivot, divide it by the radius of the pulley, and that'll tell us the angular acceleration of the entire pulley wheel. So that's one of our variables. The next one is the torque. Well, here's a little diagram, right, of what we're seeing. This is the force of tension here, right, and the string is applying a torque to the outside of the wheel. Torque, remember, is RF sine theta. R is the distance from the axis of rotation to the point of application of the force. Well, isn't that distance from the axis of rotation to the point of application of the force, which is where the string touches the wheel, the radius of the wheel? And again, that's given to you in the lab. The force that's being applied here is the force of tension in the string, of course, right, which we can calculate now. That was on the previous screen. So we know how to calculate that by using the acceleration of the masses that we can get from the lab. So then what's the angle in between? Well, let me draw in R, right? R goes from the axis of rotation to the point of application of the force. And what do you notice is the angle? Well, if the string is actually coming off tangent to the circle, and it certainly looks like that in the picture, right? And that's why we use the tangential component of the acceleration over here. Then what's the angle in between? Tangent means 90 degrees. And what's the sine of 90? 1. So the torque can be calculated by taking the radius of the wheel and multiplying by the force of tension. Now you're going to see on your lab sheet, I kind of broke it down, and I gave you all these equations on the lab sheet to help you out too, right? But I kind of broke it down by in the data tables. Right? There's the one for what you're actually taking inside of the video, and then there's one where you're calculating the linear acceleration of the masses, right? The angular acceleration of the pulley, or the force of tension, right? The angular acceleration of the wheel, and then the torque acting on the wheel. And then you're going to graph torque versus angular acceleration. Torque on the vertical axis, angular acceleration on the horizontal axis, right? And see what happens. What's the relationship, right? What's the slope? And we're going to pull meaning out of that in the post lab. Okay? Now make sure when you find that, when you finish your lab sheet, that you go back to your pivot and you answer the final multiple choice question. The final multiple choice question asks you what your slope is. Okay? Because that way you can confirm that you actually got the data right, which actually in this case probably isn't the hardest part. It's doing all the calculations right and not making any mistakes, right? But if you get weird points, that's probably why. Go back and check your calculations all the time. And then if you have to, I did add a key onto your fully remote page, schedule page, right? So that you can check things over if you have to. But see if you can do it without, checking the key along the way. A lot of calculations though, all right? In class, they're kind of doing this in a slightly different order. They're actually getting the angular acceleration because our rotary motion sensor can make angular velocity time graphs, the slope of which is the angular acceleration. Right? So in their lab, they're actually measuring the angular acceleration, then plugging it in here to find the acceleration of the masses into the tension equation we had on the previous screen to find the tension in the string, and then they can plug it into here to find the torque. So they have to do all the same calculations, but in a different order, because they have different equipment to use. Okay? Yours is a little lower tech way of figuring out the acceleration by measuring a time. I mean, because you could do this in real life, right? You could like figure out how far it was above the table, say, and then use a stopwatch to figure out how long it takes to get to the table, right? Ours is a little more precise because we're using a video, high-speed video, right? We can go at fractions of a second a frame, but it's the same kind of idea. In class, we're just going a little more high-tech. And along the way, we're hoping to come up with a Newton's second law for rotation.